Detective Euler stumbled across another peculiar equation requiring some kind of a substitution to solve. So if we notice we have some y's over x's, then we have something like y over x. We can call that equal to u. And if we do that, then we have something like y equals ux. Then we can take dy, and we have to use the product rule over here. We can say u dx plus x du. Now we can just plug this over here, and we can say that u dx plus x du over the dx, because that's what dy is, that's going to equal y squared minus x squared over xy. But we know that y is equal to ux, so we'll put like u squared x squared minus the x squared divided by the x, and then there's a ux there, so it'll be like x squared times u. And so we can see how this right side can sort of simplify and become x squared and then u squared minus 1. And on the bottom we have x squared and a u. We can cancel out these x squareds. And over here we can sort of resolve this a little bit. And we can get something like u plus x du over dx is equal to u squared minus 1 over u. Now here's how we have to be really careful, because we might be tempted to rearrange this and try to solve this like x du over dx plus the u equals u squared minus 1 over u, because this looks like a first order linear equation. But the problem is this right side over here, well, q of x cannot have the dependent variable, which in this case is u, so it can't have the u's here. It can't have the y's because it's a function of x. So this stuff here, we have to get rid of these u's and put them over there. And so in order to do that, well, let's just subtract u over. So we get something like x du over dx equals, say, u squared minus 1 over u. Then we could subtract u. But I know that I want a common denominator here, so I'm going to multiply both of this by u, so we get u squared over u. It's the same thing as saying u. And then we can sort of combine this, and we can get u squared minus the u squared. We just get a negative 1 over u, and that's supposed to be equal to x du over dx. Well, see, now we can actually separate this out, and we could say, okay, so x du is equal to negative 1 over u dx. And then we could flip this around and say that u du equals negative 1 over x dx. And now we could solve this by integrating both sides. Now we can see how there was no need to do any kind of integrating factor over here. This was actually a separable equation. And from here, we just have to basically say, okay, u squared over 2 is going to be equal to the negative ln of x plus c. And at this point, we can basically multiply this by 2 across. We like u squared equals negative 2 ln of x plus c. Now let's just replace this u squared with y squared over x squared. And that's going to be equal to the negative 2 ln absolute value plus c. Let's multiply both sides by the x squared. So negative 2x squared ln of x plus cx squared. And then we can essentially take the square root of that. So our final answer is going to be y equals negative 2x squared ln of that's the value of x plus cx squared. And we can square root this whole thing. We can even get rid of these x's and rearrange this a little bit, so we'll have something like y equals x times the square root of c minus 2 ln of the value of x. And there we go. Some crazy answer.